Hello, I'm here. Welcome back, everyone. Again, we start from a question. You can start answering your answer. Before I forget. Finally, the break is over. It was so boring, right? Well, 27, 28. Can you hear me? Yes. Okay, thanks. Just testing. Well, so what about the first one? Why would it be pointing to the right? There's no information which can be used to say anything about the direction. So speed is constant. That's the mathematical statement. And, well, velocity, speed and velocity, what's the difference between the speed and velocity? According to the definition, exactly, speed is the magnitude of the velocity. So this little v represents a velocity, which is a vector. And the magnitude of a vector is just a number. So that number is constant. So that's the only thing we know. The magnitude doesn't change. In this situation, if the magnitude doesn't change, we only have a fork. Yeah, we have to choose between two options. Number one, the direction also doesn't change. The direction also is constant. Which makes whole velocity to be constant. Or the direction changes. So we would need some additional information. There is no additional information. So we can't make a choice. So trajectory is a square. That's clearly a distractor. I want to see how many people pressed for. And all of the above that can't work because they're contradictory statements. So basically, these are kind of natural choices. If you're not sure, you know, between 2 and 5, right? Let's see. 2 and 5, yeah. Well, how can we check if we're right or wrong? Well, we can answer the same question backwards. Let's assume that the acceleration is 0. This assumption tells us that velocity has to be equal to 0, velocity. But it doesn't tell us that magnitude also has to be equal to I mean, velocity has to be a constant, but that would mean strictly linear motion. And as we know from the past, if we take a ball on a string and we make it move with constant speed, this motion fulfills the condition. Yeah. But in this situation, the acceleration is not zero. It actually points to the center. Its magnitude equals v squared divided by the radius of the circle. So we can't choose two. Not enough information. So the right answer is 5. This is a review, just to refresh the connections between velocity and speed, velocity and acceleration. That was the last slide before we left. We started talking about circular motion, horizontal circular motion. What you're going to do if you want to make a turn. Yeah. If you've watched, if you watched lots of action movies, you can see what's happening to the car if it well, encounters icy surface. So it doesn't matter what's happening to your wheels; it just keeps traveling straight ahead. So to make a turn, friction has to work. And in this situation, so to make this turn, this friction has to be responsible for the centripetal acceleration. If we cut the friction, in that case, it's like cutting the string. It will immediately just keep going straight ahead. That's all we need to know. So now we can solve a specific problem. We just need to draw, again, free body diagram. Remember, all problems very similar to problems we've solved before using Newton's second law. We just have to use one additional equation related to the centripetal acceleration. So normally, two views are helpful. So if you're looking from the top, yeah, like you in a helicopter, yeah. I don't know why, but maybe you just have a helicopter. And if you're looking down, you're seeing, well, it has to be a circle, not oval. So you see something like this. Let's say it actually makes several turns, so you can actually see the trajectory. And if we make a snapshot, a photograph right here, right now, this is a car, and well, as we said, there has to be a force of friction acting on it. There is normal force and force of gravity, but we can't see them. From that perspective, normal force points at us, and force of gravity points away from us into the ground. So that's the top view. So we don't see those forces. We don't really need them. But the side view would show a car. And now we can add those two forces, the force of gravity, the normal force. And here, again, the same force of friction acting to the center, at the center. And normal and gravity cancel each other out. And the Newton's law tells us this. That's it. Well, that's what we know about the acceleration. And what do we know about the force of static friction? In general, it can have any value between 0 and the maximum. So in general, that should be less or equal to the normal force. That's what we know about actual value of the static friction. So in general, this should be less or equal to the coefficient of friction times the normal force, and normal force has the same magnitude as the force of gravity has. So turns out m cancels, and the expression we can write which relates these variables is this. So we have 4 variables involved: speed, coefficient of friction, the radius of the circle, and g, well, 9.8 or roughly 10. And if this condition is correct for that particular situation, it does make a turn, keeping that speed, making the circle of the given radius. What's going to happen, well, if this condition doesn't work anymore? Well, first of all, these are all critical values: critical speed, or critical coefficient, or critical radius. Critical means it finally equals to 1. That's what the critical means. So what's going to happen if the actual speed exceeds this limit? If the actual speed is above that critical value, in that case, well, friction is not sufficient anymore to make it the same, the circle of this radius. So it's going to skid away and going to move, making a larger turn, you know. So here we have specific values to check. For example, let's say the coefficient is 0.05, which actually a very, very small number. So it's like a very slippery road. And a coefficient of static friction normally is, well, close to 1. Technically, it could have been even larger, but so 0.05 is a very, very low coefficient, so almost no friction. And we want to make a turn of 50 meters in radius. Oh, 50 meters, it's like 48 yards, so something like that. No, actually, 52 yards, something like that. So we can solve this equation for the critical speed. Is going to be equal to square root of 0.05 times 50 times 10. What does it give us? It should give us 5. Yeah. But that's meters per second. It's not very intuitive. So let's convert it into miles per hour and just get the feeling. So there's going to be 5. 1 mile is about 1,600 meters. So 1 meter is about 1/1600th of a mile. And 1 hour equals 3,600 seconds. So 1 second is 1/3600th of an hour. So 5 times 3,600 divided by 1,600. That's what we need to calculate. It's going to be miles per hour. You can calculate. I just want a rough estimation. A rough estimation tells me, well, I can cross 2 zeros here and here. And 16 is almost 18, very close. And 36 over 18 is almost 2. So this is close to 5 times 2, about 10 miles per hour. Well, actually, it should be less than that. So no, a little bit more than that. So 10 miles per hour, of course, it's a very slow driving. See? So if you have a very slippery road and you want to make a turn like that, you have to drive slowly. I haven't been speaking English for almost 10 days, so it's coming back to me. Any questions? Again, straightforward application of Newton's laws. Free body diagram plus centripetal acceleration. Well, a different situation. It could have been a race, bicyclist, cars, doesn't matter. So that's what's happening. And I want to ask you this question. So you have to draw a free body diagram, and you have to tell me what you think about the normal force. Normal force. Of course, since the whole problem is just a straightforward application of the Newton's second law, everything depends on how we draw the free body diagram and how we relate forces. So this is not a free body diagram. That's a photograph, yeah, a snapshot, a picture. Free body diagram should show forces and the acceleration of that object. Well, I don't know what to say when people cough. You know, when people sneeze, you say bless you, but when they cough, what do you say? Nothing? That's rude. So we can start together. The direction of the force of gravity, always the same, always straight down. Now, the direction of the normal force, well, what is the rule? What is the definition of the normal force? How does it point? How does it point? How do we describe it in words? Exactly. So there is no trick about this situation. So the most important question now is, well, how do we use this picture to calculate its magnitude? Well, I had 72 before, so I'm going to give you 15 more seconds, please. It's time to make your mind. Oops, what happened? Okay. Caring people helps. Three more seconds. Okay. There is a difference between what's happening here and what used to happen when a box was sliding down the ramp. What's the difference between the box sliding down the ramp and this case? Anyone, please make a suggestion. What? You see, this is a snapshot of the box sliding down the ramp. Gravity, normal. And this is the snapshot of this car making a circle, gravity, normal. Is there any difference between these two cases? Please. Yes? No, the car doesn't slide down. If you watched I'm not sure, probably Olympics or World Cups, you know, when a team of racer, they race, making circles again and again and again and again and again. So when they actually and they make it turn, they actually look like this. So that would be the picture of that person traveling. That person is not vertical. It's angled. It's actually perpendicular because that's the optimal, situation to keep racing as fast as possible, depending on this angle. This is exactly the same situation. There is a force of gravity acting down, and there's normal force like that. That's what the optimal means. In this situation, we don't actually need any friction to keep it moving. We can assume that there is no friction at all. It just moves again and again and again, making the same circle. So in terms of the forces, pictures look the same. There is one more physical quantity which always has to be a part of the free body diagram, and it's missing in all these three pictures. What is that quantity? There is no force of friction. We could have added force of friction, but that wouldn't make any difference for the optimal situation. Not optimal situation would mean this is not 90, that would be this or this, and friction would be involved. But when it's at 90 degrees, friction doesn't matter. We can, well, it matters to make it, that's a different kind of friction, of course. It matters to make it move, yeah. But it doesn't matter relative to skidding away up or down. It doesn't matter. So there is no friction, only gravity and normal. And what else? What else is missing? Say something. Velocity. Velocity points. Well, in this situation, if we imagine how it's moving, velocity points away from us in all cases, but velocity is not a part of the Newton's second law. What is the part of the Newton's second law? Acceleration. So all three pictures missing the same physical quantity. They miss acceleration. So please add to your free body diagram, well, actually to both, the acceleration. What is the direction of the acceleration for the box sliding down the ramp? And what is the acceleration of this car making circles, horizontal circles? So you should copy, well, that doesn't matter. It's the same. This and this is the same from a physical point of view. But these are different. So please copy. I'm going to give you 2 more minutes to take out your phone, actually photograph a picture and send it to me. I want it. So this is the box sliding down a ramp. And this is a car or actually, that's a wrong word to spell for me. This is what it is. Taking circles, well, actually horizontal circles. A car. So I need your pictures, and well, I'm expecting people start moving. You can't telepathically send me a picture. No, that's unfortunately impossible. So you actually got to take a snapshot and email it to me. And of course, the difference in acceleration matters. Yeah. So for example, you don't have to send it now, you know. It's if you have a picture, if you have a snapshot, you have like 30 more minutes before the lecture ends. But you need to do that. You have to send it to me. And well, what about the picture on the right? Are you working on it? Okay. A word of advice. There is a rule of thumb, not the law, about drawing pictures. A good picture is a big picture. Small picture is just not a good thing, you know. It doesn't help you. A good picture should take about a quarter of a page at least. That's a good picture. All right. And now I'm gonna, so since this is a very important point, so this is the acceleration for the box sliding down the ramp. Any questions about this? So the only situation which kind of interesting is here. And of course, well, what options do we have? Something like this. I call them 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So now I want to collect your responses. Technically, you can switch your answer, you know. Your what? The direction of the acceleration. This acceleration here. This acceleration here has a specific direction. It points somewhere. So your picture should show that arrow, and your button, which you press now, should correspond to the picture you're sending, ideally. But who knows, maybe suddenly you realized your picture was wrong and you want to change your mind. Okay, fine, let's see. So these arrows represent possible options for this acceleration. Of course, to help us to see what's happening, we might draw another additional arrow. That's what we call the displacement. Or a trajectory. Yeah. The trajectory is the line which demonstrates the path of that object. How does it move? Well, for the box sliding down, the trajectory is a straight line. Now here, again, you have to see what's happening. It's making turns. It's making circular motion again and again. So the trajectory of this car is not a straight line. It's a circle. And we cannot see this circle using the side view. The top view should help us. Again, if you had a helicopter hovering above it, and you would be looking down, what you would see a car making, well, an actual circle like this. That's the top view. That's the car. At every instant, the acceleration of this car must be directed towards the center of this circle. So we could have imagined something like this. Yeah. The side view, that's a three-dimensional picture. That's what makes it hard, because we're not used to manipulate with three-dimensional objects. But it's a very good skill, especially for people who want to read several slices of MRI and imagine what's happening into the whole brain. Yeah. That's a decomposition of three-dimensional situation into two-dimensional representations, and you have to decompose it back. So in this situation, that would be the center of the circle. So the object is here. That's the center of the circle. By a definition, the acceleration points towards the center. And what is for? You see, the most popular answer was related to a different physical situation. Sliding down, making circles, different physics. So now, in this case, in this situation, the normal force is indeed equal to mg times cosine theta. But in this situation, well, strictly speaking, you have to solve it now and see if any of these expressions would work. None. So let's just solve it. Let's just solve it. I have a slide. So let's just solve it. So now we know what to do. And now, again, we know how important it is to draw the acceleration. Now, I could have drawn the normal force short like this, or like this, or like this. How do I know where should I stop? Well, MA equals mg plus F normal. That's the Newton's second law. The acceleration, as we just said, must be directed towards the center. That's the acceleration. So if we're multiplying acceleration by the mass, which is a positive number, ma points horizontally to the left. Well, at that instant, again, that's a snapshot. At different instances, it will be point slightly differently, but always towards the center. That should be the gravity, and that should be that normal force. Well, the simplest way is just to do that. So this plus normal should give this. So clearly, that arrow is too short yet. That arrow would be too long. So that arrow has the magnitude of the normal force acting on this car. Make it longer. We could have do it differently. This equals this plus a question mark. How do we solve this equation for the question mark? So this minus this equals question mark, or the question mark will be equal to this plus the opposite of that, or this MA plus this mg F normal. Of course, there is another way to do it. We don't have to use triangles. We could have used components. In that case, we should have chosen x and y axis. And normally, well, we don't want acceleration having two components. So normally, we choose one axis parallel to the acceleration and another, well, at 90 degrees. So now, acceleration has only x component. Gravity has only y component. Well, normal force now has both components, x and y, but they're related. That's normal. The x component of the normal force should be equal to ma, but the y component of the normal force should cancel gravity. That's another way to write it down. I personally prefer using triangles. It's easier to me. For example, from this triangle, now I just need the angles. So this is theta. That's 90 minus theta. That's theta, theta. So that should be theta. Same direction here. Actually, no. So this, oh, actually, yes, yeah. Vertical and gravity normal. Yeah, gravity normal. Okay. So now we're golden. First of all, we can immediately write that MA over MG in this triangle equals what function? Anyone? Tangent, exactly. Tangent. Tangent of that angle. M cancels. So hence, v squared divided by r, that's acceleration g, equals the tangent of this angle. That relates all variables. So if what's going to happen if we're speeding up? In that case, if we're speeding up, the radius of the circle increases. So it will reach a new equilibrium position, and we'll be making circles of larger radius. If it slows down, the radius decreases. And finally, for the normal force, well, normal force is a hypotenuse. So in this situation, mg will be equal to the normal force times cosine of theta. So for the normal force, we get a weird expression. But it's only weird because we haven't seen it before, because we used to think it's always equal to mg cosine. Well, always put an object sliding down. If the object is not sliding, that's a completely different situation. Circular motion is different from linear motion, and one of the difference, well, on the screen. And well, we can calculate, don't care about numbers. We have an example of the solution, better writing. So again, for this situation, to keep the optimal speed, we don't need any friction to be involved. Even without friction, well, friction could have helped, but even without friction, it will be making circular motion, uniform circular motion. Speed remains constant. A lot of practical applications, of course, not just taking the turns when you race. Every train has wheels like that, and well, those flanges, they prevent wheels from sliding off the tracks, of course. But what is important, if you want to make a turn, and if you keep it flat, the stress acting on the axle might be so strong it will break it. So that's why well, at least for speedy trains, you always bank, you always angle the rails. So for each turn like that, there is the optimal speed, which leads to the minimal stress on those structures, on those axles. And if that speed is exceeded, well, catastrophe might happen. All right, I'm going to ask you this question because I need some time to prepare this demonstration. It's again about the direction of the acceleration. This is a snapshot. This is a photograph. The instantaneous position of this ball. Careful. That's what's happening. No. Yeah. It makes in circular motion, horizontal circular motion. Uniform, because speed remains constant. There's almost no friction. And we take a snapshot when the ball is here, at this location. So what I want you to tell me what's supposed to be the direction of the acceleration of this ball at that instant. So now, remember your answer and keep pressing. So write down, I'm pressing and keep pressing. I'm switching to the next slide. I'm not going to ask this question. I just want to discuss this situation. So it's kind of dangerous. You know, people used be hit by this ball. Oops. No, not good. I'm too scared. All right. Now it reaches some equilibrium. And, well, that's let's say, case number one. And that's the case number two. So the only difference is, well, speed, the radius of the circle, but the objects are exactly the same. So if I want to ask you, 69, please, 69, 12 more presses. So if I want to ask anybody, what do you think about the tension, case 1 and case 2? Same or different, and if different, stronger or weaker? You said? Why? What do you think? Same. So to answer this question, well, in general, to answer all problems, all possible questions related to this situation, we need 3 body diagrams. In general, 2 for each. So this is G, this is tension. This is little mg, and this is tension. Well, the first, the circling ball is moving. It's kind of hard to analyze at this point. But this one is at rest, which means magnitude of the tension equals the magnitude of the force of gravity acting on that weight, big M times G. And same here. The magnitude of the tension should be equal to the magnitude of the force of gravity acting on it. And because that's the same exactly weight, doesn't matter if it's lower or higher, the tension has to be the same in both cases. What's the difference? Well, the radius here and the speed here, the radius here and the speed here. So now, of course, it's time to basically just solve the problem about that ball moving in a circle. So let's see what you've answered for the direction. What was it? Of course, now we know circular motion. We have to visualize that circle, that the center acceleration must be directed at the center of this circle. We have to see it. That's it. All right. So now, well, this is a particular example. It doesn't matter what we know and what we don't know. It doesn't matter. Yeah. We have a set of variables related, and we just have to write equations for that particular set of variables. What are those variables? Well, there is force of gravity, so M is one of the variables. There is a force of tension. T is another. In this particular situation, there is also a string attached to it, which is 1.4 meters long. So there's length. Where else? Well, the angle. Well, in this weird problem, the angle is measured from the horizontal. Normally, the angle would have been measured between the vertical direction and the string. So let's call it alpha. And that is theta, and theta plus alpha equal 90 degrees. So it doesn't really matter which angle we know or looking for, it doesn't matter. So, but there is an angle, some kind of angle. Of course, there is the radius of the circle it makes. That's it. These are the variables related. So let's relate them. Well, first of all, we see a large triangle. The string, the radius, yeah, this is a right angle triangle. The length, the radius, this is alpha, this is theta, wherever you like. So, for example, we can write that R will be equal to the hypotenuse times, well, sine of alpha, or the hypotenuse times cosine of theta. No physics is involved yet, just pure geometry. Now forces, again, we have options. We can use components, we can use triangles. Doesn't matter. It's up to you. You know my preference is using what? Triangles, yes, of course. I see faster way to solve the problem. And what triangles do we have? Well, acceleration also should be here. And acceleration is related to speed, okay. So tension plus gravity equals, well, tension plus gravity equals m times a. This arrow plus that arrow should give me is it the correct representation of MA, of the centripetal force, so-called? No. What's wrong with that? Wrong direction. What about this one? Wrong direction. We know that acceleration should be horizontal. That's MA. Tension plus gravity should be equal to MA. So this is too short. We should keep drawing. This is too long. So we should stop here because our M times A, the centripetal force, should be horizontal. Now we're done. That's my alpha. That's theta. That's a right angle triangle. So mg over, no, usually it's ma. It doesn't matter, but ma over mg will be equal to, well, tangent of alpha, for example. M cancels, v squared divided by r. I use a little r. That's the acceleration. G equals tangent of alpha. That's one relationship we can use immediately. And another one for the tension, yeah, just a second. Mg divided by tension will be equal to, let's say, cosine of alpha. So this particular problem has the answer. We're going to do a couple of more examples on Wednesday, and then we're going to move on to gravity. Well, if you have any questions, please send me an email or visit my office hours or anybody's office hours. Thank you very much. Yes.
I accidentally dropped the paper, but I did do the.
Okay.
So
Just
okay, sure. Thank. So I just write down.
just write your name. Today is 16th.
Okay.
And write video ID.
Oh, okay.
Write publicly.
Okay.
Yeah.
not much election.